to my first video. Today I'll be covering my paper that I've posted on the shortest distance between an ellipse and a line. So the way this is going to work is I'm going to split it up into three separate sections. This first section will be a background section, followed by the main proof section, and we will conclude with a discussion of the algorithm, which is the Java implementation of finding the shortest distance between an ellipse and a line. So the way we're going to approach this problem is we're going to compare it to a comparable problem, which is much simpler. So how would we find the shortest distance between an arbitrary circle and arbitrary line? So the way that this is going to work is I've drawn it out here. I've drawn an arbitrary circle and an arbitrary line, and this the point on this circle that is closest to this line is simply found by dropping the altitude from the center of the circle down to the line, and then finding the intersection point of that altitude with the circle. And intuitively, it is obvious that this is the closest point on the circle to the line. But how would we prove that formally? That's the question. So the way we would go about doing that is we would translate both the circle and the line here to say the origin, such that the center of the circle coincides with the origin, I should say. And then we're going to perform a rotation about the origin, which is not going to affect the circle because circle is rotationally symmetric, but rather it's going to change the orientation of the line so that the line becomes vertical. So whatever rotation needed, such that the line becomes vertical. So following this transformation, and this is a completely isometric transformation, by the way, because we're just translating and rotating. Following that, we're going to get something that looks like this. So we're going to have a circle. No, that's not a circle. We are going to have a circle, and then we are going to have a line, which will be vertical. That's about as vertical as I can get it. Yeah, it's going to look something like this. So once again, I'm going to draw in the center of this circle, which is now it is currently the origin, because we've translated the entire graph to the origin. So I'm going to start at this center, and I'm going to drop the altitude right there, and now let's take a look at what happens. So we are going to compare this distance right here to the distance from, let's say, this point right here to the line. So if we dropped an altitude from this point to our arbitrary line, it would look something like this. There we go. So clearly, just looking at this diagram again, it's fairly obvious that this is going to be the shortest, the closest point to the line that is on the circle. But the way we're going to prove this is first let's say that the equation of this line is something like x equals c for some constant c. So let's say that the radius for the circle is r. Let's draw this segment right here. So that's also r, and let's drop this altitude. Let's call this angle theta. So so the idea here is that the distance from this center point to this right here is going to be simply c, right? but the idea is that this point right here has an x-coordinate of r cosine of theta, right? But if we want it to get from this x-coordinate to this x-coordinate, which x-coordinate is c, then this distance right here has to be c minus r cosine of theta, this distance right here. And in fact, this really holds for any terminal angle theta, so we can pretty much choose any point on the circle. So this becomes a matter of minimizing the function f of theta equals c minus r cosine of theta. And this is fairly easy to minimize. Obviously, we want to maximize this term right here, and the maximum occurs when theta is equal to 0, which is when cosine is equal to 1, so this entire expression becomes c minus r. And that is in fact the minimal distance, and we have shown that the minimal distance occurs when theta is equal to 0. So that implies that our terminal point is just the one that is collinear with the foot of the altitude from the center to the arbitrary line and the center itself. So now we have proven this this fairly simple or intuitively obvious theorem. Let's proceed further. So what we're going to actually do is we're going to generalize this result to ellipses. But first, in order to do that, we need to prove a certain theorem, which is the point on the graph of a differentiable function f of x that is closest to some line that does not intercept or asymptotically approach f is the point of tangency for a tangent line that is parallel to L. So what I mean by that is, suppose we have some differentiable function. I'll draw the graph of this function. It will look something like this. So, or those are the coordinate axes, and this is, let's say this is our function. Actually, yeah, no, let's just do a simple quadratic function. And we have our nice quadratic function, and then we also have our line, our arbitrary line. So what this theorem states is that given this differentiable function here and this arbitrary line here, the point on this function that is closest to the line is going to be the point such that at that point the slope of the tangent line is actually equal to the slope of the given line. So in this case, we can try to guesstimate it as being something like that. And my drawing doesn't even touch the parabola, but you get the idea. It would be this point right here. So if we drew this, now we see that the perpendicular, this line is perpendicular to both of these because these two lines are parallel. That is, the slope of the tangent line at the point that is closest to the arbitrary line is in fact equal to the slope of the arbitrary line. So how would we go about proving this? It requires some calculus, but first we are going to have to find an expression for the distance between a point and a line. So for sake of argument, let us call the point that we want, the point that we want to find the distance from, let's call that x0, comma f of x0. And let us call this arbitrary line, let's just call that ax plus by equals c. And let's let p be the point with this coordinate, so in this case p would be right here. and we are going to call S the point on the line. It's going to be some point on this line. So if we want PS, the distance PS, to be minimized, then S is going to have to be the foot of this altitude here. In other words, this is going to have to be a right angle. You can't have S somewhere over here, and the reason why is, oh, that's a terrible, sorry. Yeah, you get the idea. So the reason why is, if S were over here, considering that this is a right angle triangle right here, we see that PS is actually the hypotenuse of this right angle triangle. So any PS that is not the degenerate case of PS actually, the hypotenuse actually being the leg, is going to yield a result where PS is greater than the minimal result, which is the leg, because the leg of a right triangle is lesser than the hypotenuse in all non-degenerate cases. So given that, we're going to find the equation of the line that's perpendicular to the given line and passes through the point with the coordinate x0, comma f of x0, which is point P. So rearranging this equation, we have y equals negative ax over b plus c over b. And so obviously any line perpendicular to this is going to have a slope of b over a, and so we're going to have y equals b over ax plus k for some constant k, and if you plug in the point x0 comma f of x0, and let's actually call, for sake of argument, let's call f of x0, let's call that y0, and that's going to clear things up a bit. If we do that, it turns out that the equation of the line, just plugging in this coordinate, solving for k, and then rewriting it, we get this this equation right here: y equals b over a x minus b over a x0 plus y0. So this right here is the equation of the line that is perpendicular to the given line and also passes through point P. That's this right here. Okay, so given this equation, and given the equation of the given line, we're going to find the coordinate of S, which is right here. So what that is, that basically just amounts to solving this system right here. So this system, ax plus by equals c, because that's the equation of the given line, and the equation of our perpendicular line, which is y equals b over a x minus b over a x0 plus y0. So this is a simple, two variable linear system of linear equations. So the solution, I'm not going to work it out. I'll let you know the solution is x equals this quantity right here, AC. Let's scroll down a bit. AC minus AB y0, and it's plus b squared x0, and the denominator is a squared plus b squared. And our y coordinate is BC minus ABX0 plus a squared y0 divided by a squared plus b squared. Alright, so right away we notice that x and y, the expressions for them are very, very similar. There's obviously some degree of symmetry going on here, and hopefully we can exploit that when we find an expression for ps, the distance ps. And yes, quite simply, the easiest or most straightforward way, at least, of doing that is literally using the distance formula. So ps, and we know that s is with these coordinates and p is with the coordinates x0 comma y0. That's p. So if we write out our distance formula, that's going to be this enormous square. You know what? I'm actually going to leave out the radical for now, and write it after I write the radicand, just so I get the correct size radical. So we're going to take the difference of the x coordinates first. That's ac minus aby0 plus b squared x0 divided by a squared plus b squared, and then we're going to subtract x0. We're going to square this difference, and now we add the square of the difference of the y coordinates, and that's just going to be bc minus abx0 plus a squared y0 divided by a squared plus b squared minus y0 squared. And now I'm going to draw the radical, because there's no way I could have guesstimated how big it was going to be. So we have this enormous expression. Right, so the first matter of business is going to be, what we're going to do is we're going to get this into the same fraction as this right here by giving it a common denominator of a squared plus b squared. And we're going to do the same here, and then once we do that, we'll realize, hey, both of these have a common denominator of a squared plus b squared. So we're going to distribute the square to both the numerator and denominator of both of these fractions, and then we're going to be, once we do that, we'll be able to add the fractions. So after you do all of that, this becomes, again, I'm going to omit the radical first. This becomes ac minus aby0 minus a squared x0 squared plus bc minus abx0 minus b squared y0 squared. All of that is going to be divided by the square of a squared plus b squared. Okay, so now we can draw a radical, and our equal to sign. Alright, so our next step to simplifying this massive thing is realizing, well, hey, wait a second, all of the terms here have a common a, all of the terms here have a common b, so we can pull out a factor of a squared, because remember there's square out here and here for b squared here, and once we do that, we can also distribute the radical to the numerator and denominator separately, and in that way we knock out the square over here in the denominator. So if we do that, we get I'm going to write the numerator first, a squared times c minus by0 minus ax0 squared plus b squared times c minus a x0 minus by0 squared divided by a squared plus b squared, and there's still a square root up here. Alright, now here's the eureka moment. Notice that both of these terms, this term right here and this term right here, are equal to each other. We have c minus by0 minus ax0, c minus by0 minus ax0. So that means we can factor this out, and once we take the square root of that, since it's being squared, the entire thing just goes outside. But it is the absolute value of this term, because remember, we're taking the principal root here. So this is going to end up giving us the absolute value of c minus by0 minus ax0, okay, times the square root of a squared plus b squared divided by a squared plus b squared on the bottom, a squared plus b squared. And the final step, fairly easy. C minus by0 minus ax0, close absolute value, all of that over the square root of a squared plus b squared. So we've simplified this massive distance formula expression into this simple formula right here. And this is actually a well-known formula. It's the shortest distance between a point and a line in a 2D Cartesian system. It's well known. And this was just one of the many ways of deriving it. In my mind, it's the most straightforward way. Not necessarily the most clever, though. The common form of this equation is actually when they factor out a -1 inside the absolute value here, and then they absorb that into the absolute value. So it's usually written something like this: ax0 plus by0 minus c in the absolute value, and the bottom is still the same, square root a squared plus b squared. Alright, so we have to remember here that this is equal to ps. But we can view this actually as a function in x0, or a function of x0. In other words, we can write that ps of x0 is equal to this thing right here, ax0 plus by0 minus c divided by square root of a squared plus b squared. So what we're doing by writing this as a function of x0 is we're letting x0 run across the domain of f. So now what we're going to do is we're going to, in order to find the particular x0, in other words the particular point p, such that this function is minimized, we're going to differentiate this entire thing with respect to x0. So we actually need to split this into two cases because of this annoying absolute value here. So let's do that. Let's split this into two cases. Let's keep this up here, and let's draw this vertical line separating our two cases. So let's say case 1. So case 1 is when the argument of the absolute value is already positive. So in other words, ax0 plus by0 minus c is greater than 0. So in this case, the function is just, ps of x0 is equal to simply ax0 plus by0 minus c divided by the square root of a squared plus b squared. Alright, so now we're going to differentiate this this equation with respect to x0, and this is fairly straightforward. We have to remember though that y0 is nothing but f of x0, so it would actually be helpful if I wrote that plus b f of x0 minus c divided by the square root of a squared plus b squared. And now it actually becomes apparent that we're going to have to use chain rule here when differentiating this, but that's not a problem at all. It simply becomes ps prime of x0 is simply, we have a linear term up here, so the coefficient is the derivative, and here we have plus b times f prime of x0, and this is just constant term, and we're still dividing by a squared plus, or root a squared plus b squared. Alright, so now that we have that, we also have the ability to now set this entire thing equal to 0. So when we set this equal to 0, we're basically implying, hey, we're choosing the particular x0 such that the distance between p and s is minimized. So by setting the left-hand side of this equation to 0, we obtain f prime of x0 is equal to negative a over b. And if you'll take a look way back up here where we defined our arbitrary line to be this, notice that the slope of this line is negative a over b. So we have just proven the theorem for case 1, because we have shown that the derivative of f at x equals 0, or at x sub 0, at x equals x sub 0 is negative a over b, which is the slope of our given arbitrary line. And our the idea here is the same in case 2. It's literally just a sign flip, because in this case we have ps of x0 is equal to, it's the negated version of this equation right here, so c minus ax0 minus b times f of x0 divided by the square root of a squared plus b squared. So the derivative ends up being ps prime of x0 equals negative a minus b f prime of x0, all of that divided by the square root of a squared plus b squared. And here, when we set this equal to 0, realize we can just throw out the negative sign. It becomes absorbed in the 0. So the sign inconsistency across both the cases completely vanishes. So we see that, again, we have f prime of x0 equals negative a over b, and once again this is equal to the slope of the given arbitrary line. So so this proves our theorem. Just to recap, the shortest point, or the point that is closest to a given line on a certain differentiable curve, is the point such that the derivative of the function at that point happens to be equal to the slope of the given line that you're finding the distance to, or you're minimizing the distance to. And this actually connects with our circle problem here, because notice that, well, in this case the slope of the line is not defined because it's vertical, but for sake of argument, let's call that infinite slope. And notice that at the point that's closest, the tangent line is also vertical. So roughly, non-rigorously speaking, we can call this a line of infinite slope also. And yeah, so the slopes agree, and it doesn't really matter. To avoid this infinite slope problem, we could just rotate this thing again, so this is no longer vertical, and then we'd have finite slopes, and we would be perfectly rigorous again. So yeah, so that concludes the background section of finding the shortest distance between an ellipse and a line. So this theorem right here is going to become very useful in confirming that a method that we will develop is actually a valid method for finding the shortest distance between an ellipse and a line. Because this method, it's just like the circle method right here. It was heuristically and intuitively completely obvious. It didn't even seem like we needed a proof, but this is math. Just like that, our ellipse argument is going to be quite intuitively sound and heuristically sound, but to prove it, we are going to have to use this theorem, which states once again that the point that is closest to a given line on a certain differentiable function is going to have a tangent line such that the slope of the tangent line at that point is equal to the slope of the given line. So yeah, so that concludes this section. I will see you soon.